Hey everybody, right now we're in chapter 5.6. We're using sinusoidal functions to model something not involving angles. So for example, it could be something that has to do with the battery, something that has to do with a heartbeat, maybe tides. But right now we're going to move to a question where it's about a Ferris wheel. We're going to decipher the question as we go. So, a chair on a Ferris wheel is 8 meters high in its highest position. That's how I knew it was the max. So, this spot right here would be 8 meters. The center of a wheel starts at 4.5 meters off the ground. So, from the center to the bottom is 4.5. That would be C, the vertical shift. The ride lasts for 30 minutes, and the wheel takes 4 complete revolutions in that time. So it would take, if you divide 30 minutes by 4, it would take 7.5 minutes per revolution. Find the chair's formula in y equals a cos and such and such. So let's keep going with that period thing. So as we said, 30 minutes divided by 4 is 7.5 minutes per revolution. So that's the period. So we take that, sub it in, and equals 360 over k. And then once we do all our calculations, we're going to do approximately 0.8378. So that's our our k, sorry. Now we're going to try to find the amplitude. Now I figured out the amplitude by simply subtracting the max with the vertical shift, and I got 3.5. But a way to check it is to simply calculate the min, which is basically this part. So it's the vertical shift minus the amplitude, which is 1. And then, when you take the max minus the min over 2, which is the normal formula for calculating amplitude, you get 3.5. Now you're just going to draw it out to help me understand why we're using cos. So we know that each period takes 7.5 minutes, and the max is at 8. And we know that we're starting at the max because this wheel is at the max. So 8, and then down, and then back up to 8. So that's where you can see it's cos, it's not reflected, it's just normal. So now we're going to use the normal therefore statement. So y equals 3.5 cos, 3.5 is what we calculated up there, 0.8378 from over here, plus 4.5. Now we're going to move on to the next question. A volume of blood in the left ventricle of an average size human heart varies from a minimum of about 50 milliliters to a maximum of about 130 milliliters. Ken has an average sized heart and resting pulse of 60 beats per minute. Assume that one heartbeat represents a period. Using the sine function, model the volume of the blood in Ken's left ventricle with respect to time. So this is a lot of words. So I kind of wrote down the most important facts to me right here so that I don't have to keep looking back to the question. So from having the max and the min, we can simply calculate the amplitude. So we know that the amplitude is equal to the max minus the min over 2. So 130 minus 50 over 2 is equal to 80 over 2, which in the end is equal to 40. Now we're going to calculate the period. We know that there's 60 beats per minute, but there's assume that one heartbeat represents the period. So we know the period is equal to 1 over 60 because it's one beat, but there's 60 beats in a minute. So we know that period is equal to 360 degrees over k. We know 1 over 60 is equal to 360 degrees over k. So when you multiply these two, it's equal to k, and multiply these two, it's equal to 21,600. Pretty big number. So now we're going to sub in everything that we learned and calculated. So therefore, y equals the amplitude, which is 40, sine, because we're using a sine function, bracket 21,600 x. We don't even have to put the brackets really. And then we didn't calculate the vertical shift. We calculate the vertical shift by subtracting the max with the amplitude. So we know that the max is 130 minus 40, and that would mean the vertical shift is 90. So we put that into our final equation, which is plus 90. And that's another question you would normally see in chapter 5.6.